Now let us proceed with our discussions about the revision questions regarding the design of columns. So far we have covered the first few sub-questions. We are going to deal with the next one. The questions ask us to propose a critical load arrangement for the ground floor column B3. In order to solve this, you will need to first determine which columns that you are designing. We are talking about the ground floor column B3. Refers to the key plan. B3 means this column. It is an internal column. Now if you refers to the elevations, this will be the ground floor columns of B3. This represents the ground floor. The ground floor column will carry the loads on top of it. Coming back to the questions. The questions ask you to propose a critical load arrangement for the ground floor column. The meaning of critical load arrangement is that the load case that is likely giving you more critical conditions to the column here. You know that the column it will be more critical under the moment as compared to the axial load. Concrete is strong in compressions, but it is weak in tension. And then if you see the designs of the column, which is a square section, the effective depth of the reinforcement bar due to the bending of the column will be relatively low as compared to the beam. But if you see the area here, the cross-section area seems to be rather big. Bear in mind that for the design of the column, normally columns is more afraid with the moment. That means if we want to deal with the critical load arrangement, we will find a load conditions that is more likely to generate largest moment as possible. And then under the setting of the largest moment as possible, you get the largest axial load as possible as well. The top priority, it will be the largest moment. Having this principle understood, now let us look into the solutions. First, if you know that you need to deal with the critical load arrangement, that means you're going to play around with the maximum load and the minimum load. And when you talk about the design of the reinforcement for the column, we are referring to the axial strength and the moment. Those are classified under the ultimate limit state. Therefore, you're going to apply the factor of safety 1.35 for GK and 1.5 for QK. Now you need to deal with the maximum and the minimum load. Maximum load, you will have both GK and QK present. As for the minimum load, you will only have GK, but you don't have QK. Assuming that that particular space is not occupied. However, as long as the building is in service, the permanent actions will always be available. That's why you cannot remove the GK. Now, in order to get the maximum moment, that means you're going to play around with maximum and minimum load. It is either you have maximum here and minimum on the other side, or you have maximum and minimum in a reverse manner. Now, how do you know which side should be maximum and which side should be minimum? We will look at the beam span. You will use the longer span with the maximum load, whereas the shorter span with the minimum load. This you will have to refer to the key plan. This span is longer than this span. Therefore, you know that you're going to have the maximum load here and the minimum loads here. Having this set, you know that you are able to generate the maximum moment at the column here. Now under this setting, you're going to seek for the maximum axial load. We are designing this column, and this column is meant to carry the loads above the columns. Therefore, the rest of the members will carry the maximum load. Ultimately, this will be the critical load arrangement. Let's say now if you are designing the stump here, the critical load arrangement for the stump here, it will be maximum load here and the minimum load here. And then everything above will be the maximum load. This is going to ensure you that the maximum moment acting onto the stump, and under this setting, the maximum loads apply to the stump as well. Since this sub-questions only ask you to propose the critical load arrangement, then your solution should be something like this. Next, the questions ask you to calculate the critical loads acting onto the ground floor column B3. That means this is the extensions of the previous questions. Now the questions ask you to calculate the load acting onto this column. Now the critical load here, it will be the axial loads and the moment. You will need to determine the axial loads and the moment acting on the column here. Knowing that you're going to use the maximum and minimum loads, you need to first know the load in UDL. This we have done the calculations in our previous sub-questions. In the sub-questions C, which we have discussed in our previous videos, we have loading from the first floor and also the roof floor. On the first floor, you will have the maximum UDL and the minimum UDL. As for the roof floor, you know that you're going to apply the maximum UDL throughout. You may use this value and present it in the mode of the diagram. The loading on the roof, maximum throughout, whereas the loading at the first floor, maximum here and the minimum here. Next, we're going to calculate the axial loads acting onto the column. The calculations is based on simple assumptions, assuming the beams are simply supported over two columns at both ends, and the loads will be equally supported by both columns. Such an assumptions may not be accurate, but theoretically it should not deviate too far from the actual loads. We made such an assumptions is due to we want to make the calculations simple, especially for manual calculations, trying to make it as simple as possible. Now, if you wish to know the more accurate calculations, theoretically, you will have to go through the moment distributions methods. There are two types of moment distribution methods. One is the moment distribution methods, only considering the continuous beam. Another one, you will consider the moment distributions for the entire frame. In terms of the accuracy of the analyzed load, the moment distributions for the entire frame, I feel it would be more accurate. However, the calculation step, it will be more tedious. You may use the more simplified method, which is using the moment distributions method. For the continuous beam only, the estimations is not as accurate as you analyze the entire frame. There are also other methods. You may refer to table 3.5 in British Standard at 110 to estimate the load. However, this is covered in RC1, not in RC2. If you wish to know more, you may refer to the RC1 videos. Now let us proceed with the calculations. We use the most simplified method, assuming that half of the loads from the beams goes to this column and other half will go here. So this column will carry the load from this half plus this half plus this half and plus this half. The calculation steps is shown here. This represents the loads from the left hand side of the column, and this represents the right hand side of the column. The loads from the roof floor, we are taking the maximum UDL, multiply the beam span divided by 2. This is referring to this beam. As for this beam, the calculation step is the same, except the beam span. Same process go for the first floor. Just that now you're going to use the maximum UDL here times the beam span divided by 2. As for the right hand side, you will use the minimum UDL times the beam span divided by 2. Since the questions tell you that the loads given, it will be inclusive of the weights of the columns and all the structural elements. Therefore, you don't need to calculate the weight of the column separately. That means whatever you have calculated here, that will be the total loads carried by the column. Sum up all this, you get your total axial loads to be 66.24 kN. Next, we need to determine the moment acting onto the column. This is the columns to be designed, and there will be 2 moments taken. One on top of the column, another one at the bottom of the column. The moment on top of the column, it will be due to the loads acting onto the first floor beam, whereas the moment at the bottom of the column, it will be due to the UDL acting onto the ground floor beam. In order to acquire the critical moment, we will need to make one beams to be the maximum load, whereas another beams to be minimum load. The longer span beam will have the maximum load, and the shorter span beam will have the minimum load. This shall be the load arrangement in order to get the moment here. Now, if you wish to get the moment here, you will do the same. Maximum load at the longer span and minimum loads at the shorter span. When a beam is subjected to the uniform distributed load, there will be fixed end moment. Same goes to this side. When subjected to UDL load, assuming the joint here is continuous, there will also be a fixed end moment. This will lead to the bending moment in these directions, where the fixed end moment of both beams will counteract each other. Due to larger UDL here, a larger fixed end moment is expectable. You will need to get the balance when both fixed end moment counteract each other. This balance moment at the joint shall be shared by all the members of the joint. In order to determine the amount of moment taken by each member, we will need to determine their stiffness. The larger stiffness, the more moment taken. Since we are interested with the moment taken by the column at this end, we will need to first find the fixed end moment from both beams, get the balance, get the stiffness, and get the distribution factors in order for us to acquire the amount of moment taken by this column. With this understood, we will need to first get the stiffness of the columns as well as the beams. In order to get the stiffness, we need to first know the properties of the members. Based on the details given, the size of the column, it will be 200 times 200 throughout, from the stump, ground floor, and first floor. As for the beams, the size, it will be 200 times 450. It applies to all beams. That gives you the dimensions of the column from the stump, ground floor, and the first floor, as well as the size of the beams for the entire structure. Next, we will need to determine the effective length. The effective length of the columns, it will be determined by the clear span of the column. Let's say now we are talking about this column. The effective length, it will be the story height, which is 4 meters, minus the height of the beam, which is 450 mm. What is left over, it will be 3.55 meters. That gives you 3.55 meters effective length. You will do the same for the first floor column as well as for the stump. The effective length for the stump, it will be 1.5 meters minus 450. This gives you 1 meter and 0.5. As for the beam, this span is 6 meters and this span is 5.6 meter. That gives you 6 meters and 5.6 meters. Having the property determined, now we are interested to get the stiffness of the column. The stiffness is determined by K equals to EI per L. E stands for modulus of elasticity. I is the second moment of inertia, and L will represent the effective length. The purpose of determining the stiffness is for us to get the distribution factors. Based on the distribution factors, we can estimate the moments taken by the column. The distribution factors is calculated by this formula, which is your stiffness of the column divided by total stiffness of that particular joint. In this case, we simply assume the modulus of elasticity equals to 1. This is because eventually the modulus of elasticity will cancel out each other during the computations of the distribution factors. If you wish to substitute the actual E value, you may refer to the Eurocode table 3.1, which in this questions the concrete grade is 30. Referring to the table, grade 30 concrete, your E value, it will be 33 gigapascal. For simplicity, we just assume the modulus of elasticity equals to 1. Next, we need to determine the moment of inertia. This is obtained based on the formula BH power 3 per 12. B times H power 3 divided by 12. You will get the I here. The stiffness of the column, it will be 1 times I divided by L. You will use the same formulas for you to determine the stiffness of the beam. This stiffness represents the beam on the right hand side. whereas this stiffness represents the beams on the left hand side. Now get the I first. B times H power of 3 divided by 12, you get the I. Use the formulas of the stiffness. 1 times I divided by the L. Now if you are calculating the beams on the right hand side, the L it will be 6 meters. That means you get the I divided by L, you get this stiffness. And then use the I divided by L here, you get this stiffness. Having all the stiffness determined, let us present the stiffness in terms of the figures. This is the columns that you are designing, the ground floor column. There will be 2 ends. This joint will have the upper column, the lower column, and the left hand side and the right hand side beams. Therefore, you will need to get their stiffnesses. Now, if you are analyzing this joint here, you will need the column stiffness, the beam stiffness, and the stump stiffness. These values are obtained from the one that you have calculated earlier on. Based on the stiffness at the joint, we can work out the distribution factors. However, you will need to first be careful with the stiffness of the beam. If you observe the stiffness taken from the beam, the stiffness is multiplied with 0.5. But this 0.5 is not applicable to the column. Why is it so? This is due to the principles of the analysis of a typical joint. We mentioned about this in our chapter 1 of reinforced concrete design 2. Let's say you want to get the moment at this joint. This shall be the one. The purpose here is to get the moment at the column. We will assume half stiffness of the beams and full stiffness of the column. The other half will go for the adjacent beam. That's why the stiffness of the beams will have to be multiplied with half. Now, having the stiffness determined, we put aside the values here first. Let us first get the fixed end moment of the continuous beam. We have the beams from the right hand side and another beam on the left hand side. The UDL acting onto the beam shall give you the fixed end moment. The fixed end moment is calculated using this formula, WL squared per 12. This is the fixed end moment formula for a continuous beam. Based on the critical load arrangement, W it will be 9.79 kN per meter. The L is 6 meters, which is to be powered by 2 divided by 12. This gives you the maximum fixed end moment of 29.37 kN/meter. As for the right hand side, minimum load is assumed. That gives you 3.04 times the beam span of 5.6 power 2 divided by 12. Your fixed end moment on the right hand side, it will be 7.94 kN/meter. It means that the fixed end moment here is equals to 29.37, whereas the fixed end moment here is equals to 7.94 kN/meter. These two fixed end moments shall counteract each other. the balance, it will be the differences between the two fixed end moments, which eventually equals to 21.43. You will do the same step for the joint here. Since the keep length, it will be the same throughout the entire building. That means the same set of beam span, it will be on the right hand side and the left hand side of column B3. Ultimately, if you are determining the critical moment here, you will assume the maximum load at the longer beam span and the minimum load at the shorter beam span. Get their fixed end moment, find the balance, and you will get the same balance of the moment. Once you have the balance moment here, your next step, it will be to determine the moment taken by this end of column and this end of column. In order to do so, you will need to get the distribution factors of this end and this end. The distribution factors, it will be the stiffness of the column divided by total stiffness of all members at the joint. Remember, you need to have 0.5 to be multiplied with the stiffness of the beam. In order to get the distribution factors here, you will take this stiffness divided by the total stiffness of this joint, which is this plus this multiply 0.5 and plus this multiply 0.5. Ultimately, you get the distribution factors of 0.111. You will do the same for this end. Get this stiffness divided by total stiffness of this joint. The total stiffness, it will be this plus the stiffness of the stump plus stiffness of the beams times 0.5 and stiffness of the beam times 0.5. As the stump have a shorter span, its stiffness is relatively higher. That means the stump end here will carry more stiffness than the column M here. At the end of the day, you get the stiffness of the second end of the column, which is 0.088. In another word, the distribution factors here is 0.111 and the distribution factors here is 0.088. Based on the distribution factors, multiply with the differences of the fixed end moment, you get the moment taken by the columns. Distribution factors 0.111, multiply the differences of 21.43. You get the moment acting onto the column 2.4. And then take the distribution factors at N2, multiply the differences of the moment 21.43. You will get the moment 1.9 kilonewton meter. Now if you go back to the column here, this end the column will take 2 point something and this end the column will take 1 point something as calculated here. Now coming back to this question, you are asked to calculate the critical loads including the axial loads and the moment. The axial loads we have calculated 66.24 kilonewton. As for the moment, the top column will take 2.4 kilonewton meter and the bottom column will take 1.9 kilonewton meter. In terms of the design, you may use this as the critical load, the larger value of the two.